Hi, this is David Nguyen, co-founder and CEO of Brain Technology and inventor of the LCPC transform. In this presentation, I'm going to talk about how shape analysis of particles via the LCPC transform can improve lithium-ion batteries and other electronic materials. To start, let me make clear the main point of this presentation. That is, when you fine-tune shapes of your materials, that equates to fine-tuning their physical properties, chemical properties, and electrical properties. To begin, let's describe how the LCPC works. And I want to start with a pilot study we did on a titanium alloys. And in this study, the authors increased the concentration of oxygen going from top to bottom, and also increased the concentration of aluminum going from left to right. And as you can see here, just by visual inspection, as you increase the concentration of aluminum from left to right, the shape of particles begins to change, and the ratio of particles of different sizes begins to change. And similar effect can be seen in oxygen going from top to bottom. So how the LCPC works is, in this case, here's an example grain from the titanium alloy. We calculate the centroid, and that centroid becomes the origin of a 360-degree radial grid in which the lines are spaced every 5 degrees. This allows us to calculate every intersection of the radial lines with the shape, and then allows us to calculate the distance of every dot from the origin. And if you want, you can linearize this shape into 2 dimensions as such, after which you can apply the fast Fourier transform to obtain a frequency plot that is a multi-dimensional representation of the original shape that you started with. And if you want, you can turn this into a scalar value such that one number then represents the shape that you began with. And the simplest way to derive a scalar value is to sum all the magnitudes of every bin into one value. And that value represents that shape. I want to point out that alternatively, you can apply what's called the parallel grid system. Say in this shape, you want to measure only the left surface. You just have to define a way to objectively extract that left surface in every subject or particle, and then apply a parallel grid system that originates from a baseline. This allows you to calculate intersections and distances on which you can apply the fast Fourier transform, again, to get a frequency plot, which is a multi-dimensional representation of the shape that you began with. So for the titanium alloys, right, we turned the frequency plot of every object into one scalar value by summing all the bins, which allows us to calculate the quartiles of the distribution of each particle. And so the fourth quartile represents the largest particles, the quartile 1 represents the smallest particles, and quartiles 2 and 3 represents the mid-sized particles that the eye has a hard time distinguishing. What we found is that there's a threshold effect going from, as you increase the percentage of aluminum between 4 and 6%, there's a threshold because at 4%, if you increase oxygen, right, you have an increase in the magnitude of the particle sizes, but at 6% aluminum, increasing oxygen causes a decrease in the magnitude of particle sizes. And as a control, we did the same analysis using area to show that only quartile 2, of area measures exhibited this threshold effect when the 3 other quartiles did not, showing the superiority of measuring shape compared to area and how they are related but distinct in what they measure. We found another interesting effect in the 0.3% oxygen condition. As you increase the concentration of aluminum from 2.4 to 6%, you see a linear decrease in the magnitude of particles, clearly exhibited in 3 of the 4 quartiles. But if you compare it to area, area does not detect this linear decrease of particle area. So this goes to show that the LCPC transform measures shape in a way that's distinct from area and can measure things that area cannot, can measure what the human eye cannot see. Now quickly, I just want to compare deep learning versus the LCPC transform because this is a common question. Deep learning requires the users to define ground truth in order for it to work. The LCPC transform, however, allows the user to measure very precise gradients and thus discover new ground truth. Therefore, deep learning is good for automation of image detection and calculations. However, one of its problems is that it has low interpretability because the user doesn't always know what reasoning the model used to classify its objects. But an LCPC transform is good for discovering new subtypes, measuring what the naked eye cannot see, and its results are highly interpretable because the user knows exactly what, how, and why the shapes were measured. And lastly, the LCPC transform can be combined with deep learning. So let's move on to talk about lithium-ion batteries and how shape analysis can improve them. So this is the general structure of a lithium-ion battery. So you have the electrodes, okay, and you have a separator, and this whole system is bathed in an electrolyte solution that facilitates the transport of, or the flow of lithium ions back and forth with each charge and discharge cycle. And each of these components are ways in which lithium ions can be improved in terms of their density and other properties. I would like to highlight that something very special happens in lithium-ion batteries at this interface here of the anode and the electrolyte. That is something called the solid electrolyte interface forms. So as the lithium ions flow back and forth, chemical reactions happens that cause a material deposit to form, right, on the face of the anode. And this is important for the function of the battery, right, when it's first created. However, with each charge and discharge cycle, this SEI begins to thicken. And in fact, as it continues to thicken, it actually reduces the life of the battery. And so this is a particular area that can benefit from shape analysis for improvement. In this study, they imaged the structure of particles resulting in the solid electrolyte interface, the SEI. And here I just want to point out the various shapes of these particles. Here you have a Z shape. Here you have a square, roughly. Here you have an amorphous shape. And down here you have a elongated parallelogram, or a rectangle, roughly. And each of these shapes can be precisely measured by the LCPC transform. And area won't help you much, other than the very large ones and very small ones. But area can tell you or cannot distinguish between these very distinct shapes that often occur in ratios, because that's just how nature works. I would like to highlight that in this same study, they found these rounded square shapes, as drawn here in this cartoon, that have chiral properties. If you look at the location of the sharp corners, right, there's a left hand and right hand crystals, right, of this shape. And this is something the area simply cannot measure, that is right-handed and left-handedness, but the LCPC can. And in fact, just like shapes, the ratio of shapes in this condition, or in this reaction, there's a ratio likely a ratio between right-handed and left-handed crystals, which will likely correlate with the physical and electronic properties of the material. I just want to quickly highlight that the LCPC transform can precisely and accurately measure, right, left-handed from right-handedness. And here, example of this image where we measure the outline and we mirrored it, and we can establish rules by which we can, just simply by looking at the fast Fourier transform, the frequency plot, we can predict which hand is right, which hand is left. And as far as I know, this is the first time in history that we can measure handedness and know exactly every single rule that goes into classifying what is left and what is right-handed. Another thing I like to highlight from this electrolyte interface study is that here you see these two shapes are the same, the red and blue, but the scales are very different. Okay, and so here you can, if you keep them to their scale and measure their shapes via the LCPC, option one is to compare the shape and size simultaneously, but you can scale them to be the same height, such that when you do the LCPC on this, right, the only thing you're measuring is the difference in shape, not the difference in size. And this is something that area and volume cannot do, but the LCPC can, because shape is related but distinct from area or volume. And here, this is a study in which they modified a mixture of the electrolyte solution, and showing that that changed the deposition, the shape of the deposition of the material. And as you can see here, I just highlighted this bent shape and how it changes, right, as the electrolyte mixture changes. And I've highlighted just different shapes that are observable as these bent shapes are oriented differently in the mixture. And each of these shapes are something that the LCPC can measure very precisely, and that area and volume would be very bad at measuring. And anytime you have a particle system like this in a non-homogeneous system, it's helpful to turn each shape into a scalar value and stratify them based on their quartiles, and then compare the same quartile across different treatment conditions. Another way of measuring the shape of these micromaterials is the side profile. In this case, in electron microscopy, I've outlined the side profile of each of these three conditions. And I want to highlight the different ways of measuring here. In this case, we would use the parallel grid system, all originating from this baseline. And whether you put the baseline as the minima of each shape, or you define the baseline as the real baseline, that is the bottom edge of where the reaction began, where the materials were deposited, right? Each of these methods, option 1 and 2, will tell you something different between these two groups. And that's a very important thing to consider, because the LCPC transform is highly sensitive to minor shape changes, and it's these parameters that make a big difference in terms of getting repeatable results. And here, just to highlight another type of complexity that the LCPC can handle, right? Here, the particles that protrude at the top of the deposition layer. Here on the left, their long elongated clusters are formed. Okay, while here on the right, they form these clover clusters, right? And so while both conditions do share some amorphous shapes that are similar in size and shape, they do also have very distinct morphologies that are specific to each condition. And the LCPC can measure the distinctness of each morphology, and of course, tell you about the distribution and ratios between these different morphologies in each condition. Quickly, I just want to highlight that there are many applications of the particle analysis by the LCPC transform for designing very commonplace electronic devices, solar cells, fuel cells, LED lights, and of course chip design. And here, this is just to show you, so this was our cover photo for this presentation, and how in this study, they were able to precisely fabricate distinct shapes, right, in these nanolayers. And these shapes, to tell them apart, area won't help much, or at least give you very noisy data such that it will cause your machine learning model to be overfitted. But the LCPC transform can measure very precise gradations between very large objects, intermediate objects, and small objects. Lastly, another application is just fabrication of nanolayers and nanocrystals for electroplating, electrodeposition, and metal-assisted etching. And here, I just want to show an example of 3 distinct morphologies in this study, and how you can compare them in both the size and shape simultaneously, or you can scale them to be the same height such that you only compare shape between the two conditions. And in this study, I highlight it because there is a distinct distribution of shapes, right, in this reaction product, in these crystals. Right here, you have a rounded asymmetrical hexagon, you have an oval here, you have an elongated rectangle here, and you have a square, right? And there are gradients of each of these distinct shapes in these mixtures. And these gradients will not be detected by measuring area, length, or width, or at least those metrics will give you very noisy data that will cause overfitting of your machine learning model. But each of these shapes can be distinctly and robustly stratified, okay, through the LCPC transform. And if you're interested, I suggest you watch this video on particle analysis shapes on our use cases page, and it will tell you the depth of information that can be extracted from shapes that are very subtly different, and that shapes for which area won't tell you much information about the differences. Lastly, I want to reiterate my initial starting point. That is, when you fine-tune shapes, right, that equates to fine-tuning the physical, chemical, and electrical properties of your material. For more information, feel free to visit our website. For consulting services and software licensing, feel free to reach out to us at info@brainstechnology.com.